Happy Sunday, guys. Um, this will still be a short session. Um, the more we dive into math, the more I'm like, it's definitely been a decade. Oh, and if you're tuning in for the first time, hi, I'm Christina. This is just a study time for me, and I stream live just to hold myself accountable for showing up and being here. And there are 7 more days, so I am going to change the agenda. I think I'm going to focus on Python skills, like native Python skills, over using pandas so I can brush up on more like Pythonic coding again. Um, so I'm gonna change next week from causal inference into that because I don't well I do need to brush up on my causal modeling, but not at the moment I think. So I'm gonna do that and change all of the days. Um, but along with that, we're gonna finish up yesterday's session, and we'll go from there. So we saw QR factorization, and thankfully, this is built in if you do need to use it. It's built into SciPy. I know yesterday we watched some videos on it, but I understand what they were doing mathematically. And I guess what I'm losing in some of my like getting deeper into the more research aspects of data science where you're doing a lot of these is the why. I don't often always get that. So here we're timing the coefficients of doing it using the SciPy, and it takes a long time. Now, if we do single vector decomposition, which kind of, like I said, gives a pseudo inverse, it starts here, but then they do some fancy math and decompose it that way. It takes longer, so we went up, and then it takes shorter, so after they run it twice. But random sketching, I'm not sure why we're doing it, and I'll probably pull up the video for this notebook soon, is a time comparison. And we're looking at the rows, and we're looking at the name functions. Multi-index product. And it seems like they're just running it all and getting the output. Yep. So I'm going to pull up this video.
Wow, I just built the most amazing workflow on Monday.com.
You build your own workflow? Why? There are
vertical position of how high up the line.
Okay.
That it was, had the section. Oh, maybe not. GELSD, GE. Okay, I'll come back to this. Sorry, this is somewhere in this lesson. I have a little bit more detail about it. Oh, you know what? It's up in the matrix computation section. Okay, sorry about that. I'll find that and show that next time. But yeah, LawPack, low-level library, being called by pretty much all scientific computing libraries. So yeah, we were back here in the SciPy source code. It'll become important that we're kind of taking one of these, it says LawPack drivers, GELSD, GELSY, GELSS, and it's going to call them, yeah, down here, it's kind of this checking for the driver, and then calling that from LawPack. And so And the information we have is options, and this shows up in the comment at the top. The options are GELSD, GELSY, and GELSS. The default is GELSD. However, GELSY can be slightly faster. GELSS was used historically. It's slow but uses less memory. So this can be kind of helpful to read, and this is something that we could override if we wanted, kind of still wanted to be using SciPy's least squares, but wanted it to use a different method at this low level. And so this is also kind of, I think, interesting to see that SciPy has, at least two main options. It's not using the same algorithm necessarily all the time. And then just here, I did not get into the details of this at all. You can kind of just get like the very basic this computes the minimum norm solution to a linear least square problem using the SVD decomposition and a divide and conquer method. And so the key thing here is I didn't want you to get into the details at all, but I do want you to feel comfortable looking at SciPy's source code and, particularly at least like reading the comments in there because they can be helpful. And just to show that there are these 3 different methods that could be happening under the hood. And then I glossed over this, but we saw that it was, had this if statement. If is sparse, call these methods. If not, call these other ones. We're not going to dwell on the sparse one at all. But I wanted to say that SciPy's, and then this was happening at scikit-learn, it was calling SciPy sparse if it's sparse, the SciPy lineage normal one if it's not, that it's using yet another method for the sparse ones. And so that's something that's typically hidden from you when you're just using scikit-learn's linear regression, that these different things could be happening. So lineage.least square, here I've tried calling it and overriding, so passing in LOPAC driver GELSD, Y or S, and comparing the times on those. And so I got that GELSY was, about twice as fast as GELSD. And notice it defaults to GELSD, so that could, in this case, maybe you would want to override it and use GELSY. So it's only a 2x speed up. And I actually don't know what's going on here, but it's kind of interesting to me that GLSD is slower than GLSS, which is what it had said is like the older version that's generally slow. And these things would all depend on what problem you're doing. So if you did this on a different problem, you might get that a different method was faster. All right, so now we're going to kind of step back. So that was still using SciPy's implementation. We'll step back and kind of remember the definition of the least squares problem is we're wanting to minimize AX minus B and trying to find the best values for X to do that. Another way to think about this in linear algebra is that we're interested in where vector B is closest to the subspace spanned by A, which is called the range of A. And you kind of think of this as the projection of B onto A, because if you think about all possible vectors X, multiplying those by A give you the range of A, any possible, any vector that could be in the range, and you're trying to find the one that's closest to B. And so that can be expressed as B minus AX must be perpendicular to the subspace spanned by A. That's kind of getting from B to AX, since it's a projection, would be the perpendicular. Let me, maybe I should go to the drawing pad for that. Oh, I should wanted the other one.
I love watching my daughters find their paths in tech. At Capital One, my path in
So if we think of AX, really we've got a plane where this is A times X for all X's. Give us some two-dimensional plane. And then we've got some, so that was a bad angle. Some vector B, we're trying to find the X to minimize AX minus B. And so that's the projection of B onto AX. And that would, we could write this as AX hat is in that plane. And so then this is where, so this line here, is B minus AX hat, and that must be perpendicular to A. This is the whole plane. And I'll show, I'm going to show another 3 blue, 1 brown video in a little while. So this is kind of getting back to a more geometric way of thinking about matrices and vectors. Any questions here? Okay, so going back to the notebook, we end up with A transpose times B minus A, X hat must be 0. And this is where the normal equations come from. This is kind of the closed form solution for linear regression least squares problem. And so we could do this. I call this least squares naive. This is an approach that you would not actually want to use in practice because you're taking a matrix inverse. which you generally really want to avoid doing. But I just kind of did this as a starting point of this is something that would work. Assuming, I guess it would work assuming that A is not something we're going to end up dividing by a number close to 0 to get its inverse. Matthew, who has the microphone? Nice.
And you don't want to do the inverse because it's computationally expensive? Or?
Yeah, so it's both computationally expensive and it can also be unstable because you end up dividing by things. Yeah, good question. So here, this was just kind of a first stab at implementing something that would give us an answer for linear least squares regression. All right, so then coming off of that, these are called the normal equations, this equation we got above. And really, this equation has been rewritten, and we're just taking A transpose B, or I guess we're taking A transpose AX to the other side. So we have A transpose AX equals A transpose B. And so if A is full rank, A transpose A is going to give us if A is square, well, actually not even square. If A is full rank, we're going to get a square Hermitian positive definite matrix for A transpose A. And square Hermitian positive definite matrices have something called a Cholesky decomposition. And the Cholesky decomposition, or Cholesky factorization, finds an upper triangular matrix R such that R transpose times R equals your matrix. And what would so if R is upper triangular, what would R transpose be? Yes, lower triangular, that's correct. Not all questions I ask are hard. So what we're doing, so in this case, we're looking at A transpose A, we're gonna take the Cholesky factorization, and that'll give us back R such that A transpose A is R transpose times R. A transpose times A equals R transpose times R. Here, I've just pre-computed A transpose A since I'm going to be using it a few times, as well as A transpose B. And then I'm going to use SciPy's implementation of the Cholesky factorization. As a warning, NumPy and SciPy default to different. One of them returns the upper triangular matrix and one returns the lower triangular matrix, which I discovered the hard way. I didn't realize I was switching between NumPy and SciPy. I was like using this in other operations and getting different answers. But yeah, so we can, and so it's always good after you do this to kind of check that what you're doing makes sense. So I'm passing A transpose A in, actually let's even look at, okay, that's difficult to see. So remember, np.setPrint options is super useful. You can do suppress equals true to not show zeros in this format with an exponential 0.00 E00, which is not very readable. And then you can also set the number of digits you want to see. Although this matrix, I guess, is still kind of too large to be that viewable, but I can believe that this looks like an upper triangular matrix that I've gotten back. And then I'm just confirming that A transpose A minus R dot transpose times R is giving me something close to 0. So A transpose A is approximately equal to R dot transpose R. And so then the way that the Cholesky factorization is useful in solving the linear least squares problem is, so we can plug it in. Now we have our R instead of A. Then we have R transpose, and here I'm calling Rx, saying that equals W, which you can see in this last line, setting that equals to A transpose B, and getting Rx equals W. So why is this helpful, right? Like I've just kind of written this equation a few different ways. Why might this be better than just sticking with our A transpose A, X equals A transpose B? Oh wait, Matthew, okay, throw it.
So now it's much easier to solve the last equation because the R is like a triangular matrix.
Exactly.
So you just make a substitution, and then the same applies to the equation for X.
Exactly. Yeah. So that's it. Solving linear systems of equations for a triangular matrix is a lot easier because you just start with the last entry, divide by one thing, then you plug into the second to last entry, and so on. So it's much simpler than solving a linear system where you have a non-triangular matrix. And so we've kind of just changed this into having to solve two triangular systems of equations. So we solve, I guess we would solve this one first to find W, and then we solve the one on the last line to find X, which is our original answer. This, I think, kind of illustrates a lot of numerical linear algebra is about getting these factorizations, and often it looks like, okay, you've just rewritten the problem, you still have all these factors, but it's because of the properties of the matrices you factored into, you've made things easier for yourself in some way. Are there any questions about this or questions about why it's easier to solve a triangular system of equations? Okay, so yeah, this is just kind of rewritten the least squares linear regression problem. So here, kind of working our way towards X. First, we're going to solve the triangular system R transpose W equals A transpose B, which is what's happening in this line. And so SciPy Lineage has a solve triangular method, even where you give it a triangular matrix, and that has a transpose argument. So here we're letting it know this is our transpose. Again, we're kind of checking that our result is what we were hoping, and that R transpose times W minus A transpose B is close to 0. So we've successfully solved this third equation. And then from here, we solve triangular R with W on the right in order to get X, which I called a coefficients Cholesky here. And we got that works. And so I can put this all together in a method and say that solving least squares with the Cholesky decomposition takes in A and B, gets the Cholesky decomposition of A transpose times A, and then it solves those two triangular systems and returns the answer. Any questions? Kelsey, and you throw the microphone.
Why was this slower than the rate?
Yeah, that's a good question. So I think here, and I have to look this up, that's probably the cost of calculating the Cholesky decomposition. And so I'll check on that with you. This down. I think it's also to remember the naive way you have this instability that comes with getting the inverse, so that's kind of less good in that regard. But yeah, I'll check about the time.
Is there like some sort of like the order of it, like the size of your matrix?
Yes, yeah, I'm sure that like this is small enough that I think constant terms matter more. So when you get to like really huge matrices, it does become more about like the highest order term. But yeah, the size could matter.
The other question is, so this is not what Scikit is doing.
Correct.
Why?
So we'll come back to kind of a comparison. So I'm going to kind of show you several different ways to do it, and then we'll like compare the different methods. Yeah, good questions. Any other questions about this approach? Okay. And then I think I brought this up last week when I was looking at the history of Gaussian elimination, but the Cholesky decomposition is the one that Gauss first found, that Cholesky got the credit for. Oh, yes. Yeah, you can always walk it too.
Yeah, so I see the slide on the notes.
Back up.
We actually get two different NT dot linear log dot norm. We have different value here. One is 1.13, one is 6.86. So what has changed in these results?
So these are so close to 0 that it doesn't, like here I'm mostly trying to confirm that this is a number close to 0, and I'm interested in the exponent and wanting it to be 10 to the negative 14th is close to 0.
Okay.
Although I guess that is a question, why aren't we getting exactly 0 if this is a way to decompose and get the answer?
Right, yeah.
Or, I mean, does anyone have an answer to this on why we're not getting it? But yeah, because there's so machine epsilon, because we get rounding errors, and with floating point numbers, we're trying to represent these continuous numbers with discrete values.
Cool. Another question is, because A is actually invertible, so we normally find the best coefficient by, for example, gradient descent, right? But here we are actually trying to solve a linear algebra solution. So which way is usually faster?
So when we bring up gradient descent, are you talking about like a stochastic gradient descent approach? So stochastic, I actually originally had stochastic gradient descent in this lesson with PyTorch, and it was actually much slower than any of these linear algebra approaches, and so I took it out because it just didn't look reasonable compared to them. A benefit, so yeah, SGD will often be slower than if you have kind of like a well-studied method for your particular problem. But a benefit of SGD is that it's so general. And so if you have a problem where you don't have a closed form solution, or people haven't studied it to come up with this optimization method, you can use SGD there. So kind of the benefit of SGD is, that it's so general and that it will work on problems where we don't have closed form solutions. Connor, and can you throw the microphone? Or pass the microphone?
But I thought that like if we have say our dimensionality is like really, really, really large, then the closed form solution like takes a while in comparison. I don't know. I don't know. I was just like reading somewhere.
Yeah, no, and that's quite possible too. Yeah, that at a certain size, it might be worth it. Yeah, and that's an important note, I think, with all of these, that the answer of what algorithm is best can really depend on your problem. And we'll see that later. And so different things like both the size of your problem, kind of properties around the stability of your problem. We'll see later two methods that kind of, or two particular matrices that don't work well for a particular method. So there's a lot of variation with these. Yeah, these are good questions. Any other questions about Cholesky factorization before we go on to our next next approach. All right, so next up is the QR factorization. And this, again, next week we will actually talk about how to code a QR factorization. We're still just using NumPys. Can someone remind me what the QR decomposition gives you?
I'm kind of getting it, but isn't it 2 orthogonally the lower and first, right?
No, although you have the right words in there, but I think Kelsey has a guess.
I think it's a practical one, and then when that's orthogonal, column vector is orthonormal as well, or just one?
I believe, so if it's square, they would be orthonormal. But yeah, I guess for the non-square case, I would have to check. But yeah, so Q is orthonormal, R is upper triangular. Thank you. And where did we see the QR factorization before? I'm not sure that we saw it with NMF. Yeah, so inside of randomized SVD, we saw it. Okay, so here, so kind of getting into these equations, and next week we'll talk about how to code a QR factorization ourselves. So AX equals B, we're going to get the QR factorization for A equals QR, plug that in, and then say Rx equals Q transpose B. And why was I able to go from Q on the left side to a Q transpose on the right side? Yeah, so a few people shouted this out. Q is orthonormal, so multiplying by Q transpose, we get the identity on the left. And that's also nice because you're not having to calculate an inverse, you're just transposing columns. And then why is it nice to have Rx equals Q transpose B? Can you grab the microphone?
You want to solve for X, R is over triangular because you just solve.
Exactly, yeah. So now we have a linear system of equations with a triangular matrix that will be fast to solve. So here we do QR equals, using SciPy's QR factorization, and then we get a triangular system to solve. We solve this, and all right, we're getting the same error that we've been getting. Questions about this approach with the QR factorization?
Why is this one even slower?
The question is, why is this one slower? Well, let's actually save the timing comparison ones for a moment. But yeah, we'll come back to that. Any other questions before we start our next approach? Okay, so now yet another approach. We're going to look at SVD. And so again, we're still trying to solve the same problem of AX equals B and finding the optimal X. Now we're going to use the singular value decomposition. Can someone remind us what the singular value decomposition is? Tim?
The full SVDs will decompose the matrix since it's a product of the sigma V transposing.
Yes, yeah.
So U and D are orthonormal matrices, and sigma it contains a block of a square matrix where the diagonals are your singular values.
Exactly, yeah. So sigma is a diagonal matrix. Everything's 0 except the diagonals, and those are the singular values, and U and D are orthonormal.
Sigma doesn't have to be square though, right, in the full SVD?
So they talk about, I didn't cover this in class, they talk about like a full SVD and also a reduced SVD. And one of them it's not square, but you're just adding a bunch of zeros to get the dimensions to work out. Yeah, and actually I guess, I think for the reduced one, really it's just that U has orthonormal rows and V has orthonormal columns. And then for the full version, you're like expanding them so that they're full bases.
So in the full, U and D are square.
Yes, yeah.
In the full SVD, the U and the V are square bases.
And I'll bring Trevathan has a nice picture of this. Yeah, I'll talk about that next time. Full versus reduced for SVD. Okay, yeah, so that's the SVD, which we've seen a few times before. Here we plug that in for A, and then actually similar to what we did before, we can multiply each side by U transpose, since U transpose times U is the identity, because U has orthonormal rows. We get sigma Vx equals U transpose B. Then we have sigma W equals U transpose B, X equals V transpose W. And so this, I actually think you should kind of be seeing some common themes between these three different approaches. Well, actually, I guess first I should say, what's nice about solving sigma W equals U transpose V? Does anyone else want to answer? And so here we've just said Vx equals W, and now we're going to solve sigma W equals U transpose V. Roger? Tim, can you pass the microphone?
So it's diagonal, so why don't we just divide with the
Exactly. Yeah, so solving a diagonal system of equations is even better than solving a triangular system because you just have a single non-zero coefficient for each equation, so you can just divide through. So that's very quick to solve. And then we're left with, well, Vx equals W. Since V is orthonormal, we can rewrite that x equals V transpose W. And then this is that in equation form. So we're using SciPy's SVD here, getting back U sigma, and called it VH in this case. Then I see for W, notice I'm just dividing by sigma, dividing U transpose B by sigma. And here, I guess U transpose is possibly larger than I need, so that's why I'm chopping off the end. And then I'm returning VH transpose times W. Questions about this approach? Yeah, some people are noticing that this is much slower. We've gone from microseconds to milliseconds, which is a order of or 1,000 time difference. Any questions or questions about the equations, kind of how we solved this? And then yet another technique that I'm not going to get into detail at all on, but wanted to let you know that it's out there, is that there's something called the random sketching technique for linear regression, which involves using a random matrix and computing SA equals SB, and then finding a solution to the regression SA X equals SB. So I just wanted to let you know that that exists as an example of a randomized approach. And this would be where you had a very large A and B. Okay, so now I think you'll like this part. We're going to do a timing comparison and do it a little bit more formally. So above, we were just kind of printing out what the times were for the diabetes data set. What I'm going to do here is randomly generate some data, and M is going to be either 100, 1,000, or 10,000. N is going to be 20, 100, or 1,000. Okay, you can see down here is where I generate the data. Randomly, A has dimensions M by N. And I'm going to loop through all possible values of M and N. And then we're going to compare these different techniques. So we've got the naive solution with the normal equations, the Cholesky factorization, the QR factorization, SVD, and then also SciPy's least squares. Let me see if there's anything else about the setup. In SciPy's least squares, it returns several items, but we just wanted the first one. So that's why I've kind of wrapped it in this other method. And here I'm using, so I've got my row names, and then I have a dictionary that converts the name, kind of lists what the method is that we've defined for that. Who in here has used pandas before? Pandas, plural, yeah. Okay, so it looks like everybody. And I'm just using it here because the data frame is kind of a nice way to store a table of information. And I'm using the multi-index, which can be handy to have M and N. So now I just have a nested for loop. And this kind of formally for the linear least squares problem, you want M greater than or equal to N, like you typically have more data points than you have features. So I'm just looking at those cases. What I'm going to do is loop through them, randomly generate data of that size, so with M rows and N columns. And then for each method, I am going to get the function. I'm going to use Python's timeit module to time it. And what this will do is run the decomposition 5 times and track the speed of each one and average them. And it's good to run it a few times just to kind of reduce variation some. Then for the data frame, I'm going to set the value of that method for that row and column. This is how long it took. Oh, and then I'm interested in the error, not just the speed. So I've got the coefficients back from, this is a little tricky. So function is a string. And so timeit you actually pass a string to. Here we're using locals to kind of look up the actual variable with that name. Call that on A and B. And then check what the error is using our metrics on coefficients. And in this case, for simplicity, I decided just to look at the L2 error. So that's what I'm storing in my df error data frame. So I've got this df data frame that's going to hold the time. Df error is going to hold the error. And so I run that, and that can be a little bit slow to run. So I'm just going to use the results I have here, since it's doing kind of all these matrix decompositions, and so the matrices are larger. Actually, let me see if this will fit on the screen when it's larger. Okay, are you able to read this this table all right? Let me actually put them both up. So the top table is like perfectly fits. Top table is the time it takes, and the second table is the error. Let me spend a moment just kind of looking at this and tell me what you notice, which methods are working best, kind of in which cases. Does anyone want to share some observations? Okay, and then microphones between Aaron and Roger. I'm going to throw it to Connor.
Like across the board, in terms of timing, Wachowski factorization does pretty well.
It does, yeah. No, the Wachowski factorization does, I thought, surprisingly well. And there are much larger matrices out there that we could have done this on. Any other observations? I have to say, I was personally surprised by how slow SVD is. What do you notice about the error? Yeah, it's the same in all of these, so that's reassuring. So here, this problem is not one where we're having to worry about kind of stability with different ones. Matthew, if you go to the microphone.
Why would FGD get slower than that?
Oh, that's a good question. Yeah, I'm not sure about that. I'll think about that more. Good question. So here I just used random uniform. Oh, yeah, maybe it was like an unlucky draw. Yeah, it's random for each one. Okay, and I also wanted to kind of share this as I guess I do want to highlight that Cholesky is fast. Yeah, Cholesky's fast. A lot of these. I want to highlight this as a technique for comparing methods. I think that this can be kind of nice to do this kind of like looping through and getting data on how fast things are in a systematic manner. And it also, I think, makes it a lot easier to compare as opposed to looking, kind of having to scroll through like different places in the notebook when we just outputted one line at a time. So I think this is a good kind of good general purpose method for comparing methods.
Okay, I'm going to stop here for today. And I am going to change next week into just Pythonic review. Because as a business data scientist, I don't code algorithms that often. It's just not a part of the job description. But I think I need to review that with the changes coming to the marketplace. So I'm going to change next week over into that. And I will see you guys then. Have a great Sunday evening.